Hello students and welcome. Today we are going to look at some of the most important and frequently asked about compounds from the D block elements. Okay, let's dive right into this.
Just think about it for a moment. You add just a tiny amount of this substance, these purple crystals, and suddenly the water is cleaner. Now this isn't magic, this is pure chemistry, and it's a perfect example of a transition metal compound in action.
So, I want you to think of this session as a tour of a chemistry museum. We will be looking at a few famous masterpieces. These are specific compounds that perfectly show the unique properties of transition metals, and these are the key examples that you must know for your exams.
So, on our tour, we have 4 main exhibits lined up. First, we have the powerful potassium permanganate. Second, the vibrant potassium dichromate. Third, the beautiful copper sulfate. And finally, we will look at the 2 very different personalities of iron. So let's begin.
Our very first exhibit is a true superstar of the chemistry lab, potassium permanganate, or KMNO4. And I've given it a special name, the Purple Predator. You are about to see exactly why it has earned that title.
Now, look closely at the oxidation state of manganese here. It's at +7. That's its highest possible state. This makes it incredibly unstable and, well, hungry for electrons. This extreme oxidation state is the direct reason for its intense, deep purple color and its powerful personality as an oxidizing agent.
And that powerful electron-hungry nature? Well, that is the answer to our starting question. This is exactly why it works so well as a disinfectant. The Mn+7 state attacks and oxidizes organic matter like bacteria. As it reacts, its oxidation state gets reduced, and that beautiful purple color starts to fade away. So a fading color actually means it's working.
Now let's see how this same concept of high oxidation states plays out in our next exhibit. Let's meet another powerful compound, the orange oxidizer, potassium dichromate.
Here you can see the chromium is in a +6 oxidation state. Again, a very high state, which makes it a strong oxidizing agent, though it is slightly less aggressive than our Purple Predator. And this +6 state gives it that characteristic bright orange color.
In the laboratory, this compound is famous for its role in redox titrations. As it oxidizes another substance, the Cr6+ gets reduced to Cr3+. And this brilliantly illustrates a key property of transition metals. The color changes with the oxidation state, from a vibrant orange to a distinct green. This visible change is used to find the exact endpoint of the reaction. It's very useful.
Now to help you remember the relative strengths, I want you to think of it like medals in a competition. Potassium permanganate with manganese at +7 gets the gold medal for being the most powerful oxidizing agent. Potassium dichromate with chromium at +6 gets the silver, and as we are about to see, copper sulfate gets the bronze.
And that brings us to our third exhibit, a compound that is famous for its absolutely stunning appearance, the blue crystal, copper sulfate pentahydrate.
Here, copper is in a much more stable +2 oxidation state. It's not desperately trying to grab electrons like Mn7+ or Cr6+. You could say it's more content. This makes it a much weaker oxidizing agent, but its d-electron configuration still gives it a beautiful, vivid blue color.
Now here is a very common point of confusion among students. You might think that the blue color is simply because of the copper ion, the Cu2+, just floating around in the water, but actually that is not the complete story.
So, the crucial point here, the real secret behind that famous blue color, is something called an aqua complex. What happens is the central copper ion gets surrounded by water molecules which act as ligands. It is this entire structure, this complex, that is responsible for the color that we see.
So what's really going on is that this complex absorbs light from the red part of the spectrum. And as you know from physics, when red light is removed from white light, what we see is its complementary color, which in this case is blue. This shows that the color of a transition metal compound depends not just on the ion, but also on its coordination environment. It's a very important point.
For our final exhibit, let's look at an element that very clearly shows us 2 different personalities based on its oxidation state, and that element is iron.
Let's look at them side by side. On the left, we have iron 2 sulfate, where iron is in the +2 oxidation state, and its solutions have a pale green color. Now on the right, we have iron 3-sulfate. Here, iron is in the +3 oxidation state, and its solutions are a distinct yellow-brown. It's the same element, just one electron different, and you get a completely different color. This is the very essence of transition metal chemistry. And with that, our tour of the individual exhibits is now complete.
Okay, now let's just step back for a moment and look at the big picture from our entire tour.
Let's quickly consolidate everything we have seen. First, potassium permanganate. Remember, manganese at +7, deep purple color, key use as a powerful disinfectant. Next, we had potassium dichromate with chromium at +6, bright orange color, and it's essential for titrations. Then we had copper sulfate, copper at +2, giving that vivid blue color because of its aqua complex, and it is used as a fungicide. And finally, the iron salts, showing how Fe+2 is pale green, while Fe+3 is yellow-brown.
So what is the one core idea that you absolutely must take away from all this? It is this: a transition metal's oxidation state is the key. It directly determines the compound's color and its chemical reactivity, especially its oxidizing power.
And to help you remember their relative strengths, please always keep that metals analogy in your mind. The highest oxidation state, Mn+7, gets the gold. Cr+6 gets the silver, and the more stable Cu+2 gets the bronze. It's a simple way to remember.
And finally, always try to connect these concepts back to a real observable example. That image of those purple crystals powerfully disinfecting water, that is a perfect mental picture of a high oxidation state doing its job.
My advice to you is very simple. If you can remember the core idea about oxidation states, one mental picture like our museum tour, and one real-world example for each compound, I promise you this entire topic will feel much, much lighter for you during your exams.
And I will leave you with one final thought. We've seen that these compounds have different personalities, different colors, different reactivities. Now, how could a chemist use this knowledge to design completely new reactions, or perhaps even new materials with very specific properties? It's something to think about. Thank you for joining the tour today.